Alright, welcome back. We're on part 3 of our lecture. Now, so far we've been talking about all of this radiation modeling stuff, maybe a little too abstractly for a climate class. Let's try to put this idea a little bit more into the context of climate change by talking about, okay, remember how we built this radiation model and we ended up determining a certain flux of long-wave radiation at the surface of the Earth. We've determined from which we could infer like the temperature of the Earth or something like that. Well, you could then imagine we could take the same model, increase the amount of greenhouse gases in the atmosphere, compute new optical depths for different layers of the atmosphere, compute a new equilibrium temperature of the surface, new radiative flux at the surface of the Earth, and it would be corresponding to a new temperature. So you could have like the before amount of long-wave radiation the surface was giving off, and then, or the radiation imbalance or whatever at the surface, and you would have like the after you've added these greenhouse gases to the atmosphere. And that difference between the flux of radiation at the before and the after is what is called the radiative forcing, or the RF term in climate science. The IPCC goes to some effort to try to define this idea of radiative forcing. Their actual definition, pulled right out of the Assessment Report 5, says that it is the net change in the energy balance of the Earth due to some imposed perturbation. Now, notice that they're being very vague there about this idea of an imposed perturbation. They're not in advance telling us like what is causing this change in the radiative balance. Rather, this kind of comes to us more from theory or something like that. Like you could talk about the change in the radiative balance of the Earth due to a major volcanic eruption. Where like you could talk about like what's the net radiative balance before the eruption, and then after the eruption when all these aerosols have been put into the atmosphere and so on. And you could talk about like how there has been a change to the radiation balance due to this perturbation, in that case a volcanic eruption. And anything that changes the radiation balance of the Earth can be one of these perturbations. And in the science of climate, they talk about like radiative forcings associated with changes in the Earth's orbit, like before or after the Earth's orbit becomes more eccentric, or based on changes in the output of the sun over periods of time. They could talk about the radiative forcing caused by a change like that. The units, the way we express radiative forcing is usually in terms of watts per square meter. It's the difference in the net radiation balance at the surface of the Earth before and after that perturbation happened. So it's kind of this, average radiation balance before, average radiation balance after, and then the difference between them. And of course, because we've been adding greenhouse gases to the Earth's atmosphere, if you want to talk about the radiative forcing associated with anthropogenic greenhouse gases, then this would be, like we have increased the radiation balance at the surface of the Earth. There is a net imbalance that's due to the perturbation of us adding all these greenhouse gases by literally the gigaton. Okay, gigaton, billions of tons. So like, I forgot I had a slide here that talked about it explicitly in the context of volcanoes here on slide 49, but you could compute the energy balance under control conditions, like before the major volcanic eruption, and then after, and you could see the radiative impact of ash and sulfuric acid and greenhouse gases and so on as they were put into the Earth's atmosphere. That's a very standard thing. You pick up something like the Journal of Climate or something like that, and there'll be all kinds of articles in there about radiative forcings associated with different factors, both anthropogenic and natural. The radiative forcing is often presented as the value between these two particular times. Okay, just to articulate what we're saying here. So like you talk about before or after a certain perturbation. And while it's true that there is also a whole scientific endeavor of like how the radiative forcing changes with respect to time, like how after the volcanic eruption, as the atmosphere purges itself of all those aerosols and so on, how the radiative forcing changes with respect to time, that's in general not where we're going with this right now. Right now we're just talking about it as kind of a before and after kind of thing. Before we added all those greenhouse gases, and then after. So instantaneous radiative forcing, or RF, is a change in the radiative forcing. It's actually defined as down minus up, but I would never ask you that. In terms of long wave and short wave net radiation in watts per square meter due to this imposed change. And this imposed change results in this radiative forcing, a change in the energy balance, and that's going to result in a temperature change. But it doesn't happen just like that. By adding heat, we are gradually increasing the temperature. Okay? If you think about it as like, we put a cold pizza into the hot oven. It isn't like the pizza instantly becomes hot. there is a net, sitting on the countertop, the frozen pizza had some energy balance to it. It was slowly gaining heat as it thawed or whatever. But when you put it into the oven, now it is gaining heat. There's a large number of watts per square meter of heat going into the pizza, right? That is a change in its radiative balance, and a climate scientist would call that a radiative forcing. We have changed the radiation balance on that pizza. But that doesn't make the pizza warm up just like that. There is a change in temperature with respect to time. There's a change in temperature, delta T, that takes place over a period of time depending on the value of the radiative forcing and lambda. Now, in the context of climate science, we call lambda the climate sensitivity parameter. It's how fast the temperature changes based on that radiative forcing. Now, as far as I know, there's no pizza sensitivity factor or something like that. I mean, I'm sure generally speaking in physics, they probably have like a thermal sensitivity factor or a thermal sensitivity parameter or something like that. But basically, you know, some foods heat up faster and some foods heat up more slowly in the oven, and there would be some parameter, this climate sensitivity parameter, that would be describing how fast that pizza warms up versus the fish sticks, versus the broccoli that you have in the oven, whatever. They all warm up at different rates, even though they're all having the same radiative balance. I mean, the radiative forcing, right? They're all having this increase in radiative flux because they're in the oven. Well, the same case is true with Earth. The Earth will warm up over a period of time. So radiative forcing, which has that value, those units of watts per square meter, times this climate sensitivity parameter lambda, where lambda has units of degrees Celsius per watt per square meter. So you can see how when you multiply lambda and RF, the watts per square meter cancel out and you just get degrees Celsius. So this is the change in temperature that we will result in as we have that imposed radiative forcing. I know it's confusing that we use that symbol lambda again. That's just the nature of science as we reuse symbols. I know prior to this we were using lambda to mean wavelength. Here lambda means the climate sensitivity parameter. It's helping us know how hot the planet will get based on this much radiative forcing. Same with like how hot will the pizza get based on being put into that oven where there's this new radiative forcing. Lambda, the climate sensitivity factor, is not something we can measure. It is something that we get from like models or theory or something like that. We can come up with estimates as to how much the planet's temperature will change for every watt per square meter that we change the radiation budget based on things like greenhouse gases and so on. So this is one of the things that like those big computer models that simulate the climate of the Earth give us. They give us this climate sensitivity factor, and in fact in the IPCC they studied a large number of these big climate models, the kind of things we're going to be learning about in Module 3. But just to give you a sense of what the bad news these models tell us here, this diagram here on slide 54 that's at the top of the page is just a histogram that shows, I forget how many models they ran, maybe 50 or 60 different models they looked at their output. And they made a little histogram that computed the climate sensitivity parameter based on each of those models. Each of those models came up with an answer, and they just made a histogram of it. So like, for example, these are actually climate sensitivity parameters based on doubling of carbon dioxide in the model. And you can see that they all resulted in climate sensitivities, well, a range of them. All of them involve the planet getting warmer, doubling the amount of carbon dioxide, which we have not done yet, but we, on our present path, will do sometime in the 21st century. We see that there's a sort of a distribution to them. Most of them seem to show that doubling the amount of carbon dioxide in the Earth's atmosphere would result in a climate change. The sensitivity of the planet's temperature to that radiative forcing would be about 3 degrees Celsius, so that's a huge climate change. What I think is really scary about this, though, is that almost none of the models showed less than 2 degrees of temperature change for doubling the amount of carbon dioxide in the atmosphere. And some showed quite a lot of change. Some models showed that the sensitivity of the Earth's temperature to doubling the amount of carbon dioxide in the atmosphere was 5 degrees Celsius. Some showed 8 degrees Celsius. Some showed more than 10 degrees Celsius. And that distribution is actually quite scary. The way that is actually drawn there, that's what statisticians would call a right-skewed distribution. See how it's not like a bell-shaped curve? It sort of has a big long tail off to the right. See, what that suggests is if the amount of carbon dioxide in the Earth's atmosphere were to double, which it probably will, the probability of these very large increases in temperature, like 8 degrees Celsius, 10 degrees Celsius, 12 degrees Celsius, are larger than a small change. There's no model that showed it would only be 1 degree Celsius. There's no model that showed it would be 1.5 degrees Celsius. In fact, it looks like only one model showed less than 2. Oh, so see, while it's true that the most likely outcome is to have about 3 degrees Celsius of climate change due to doubling of carbon dioxide, it's actually non-negligible that it could be like 10 degrees Celsius. Oh, the chances of 10 degrees Celsius or more is greater than the chances of it being like 1.5 degrees Celsius or less of temperature change. That is a kind of insight that we're getting from these radiation models. We're starting to realize not only, do we get these radiation models that helped us understand the flow of the two streams of radiation moving up and down the atmosphere, it actually led to these insights of what are the range of possibilities and which ones are more likely than others. That is important. Now, again, just to focus though on this point here, climate sensitivity parameter is not something we measure, it is something we get from models. Okay? The full-blown model that takes into account changes in storm tracks and widening of the tropics and changes in ocean circulations and so on. All that good coupled model type stuff that we're going to do in the third module of the course. You have to use that full-blown model to come up with that climate sensitivity parameter, lambda. It is not something that we can just calculate based on like measurements or something like that. That is not how we can compute this climate sensitivity parameter. We're going to keep messing around with this idea of how the physics of how climate actually makes these changes happen, so that then we can, later after the spring break, we can start talking about this in terms of like how things will change in models. But this is enough for our lecture 2C. Let's go ahead and answer 3 more quick questions before we're done with this lecture. Question 7. What are the units of that climate sensitivity parameter? Watts per square meter, watts, degrees Celsius, or degrees Celsius per watt per square meter? Which of those is the units of climate sensitivity parameter? Alright, make a choice from those 4 options and get a little feedback before we move on to question 7. No, question 8 actually.